Ladies and gentlemen, please welcome Chief Technology Officer, Fujitsu Fellow, Fujitsu Imaya, Dr. Josef Rega.
Good morning, ladies and gentlemen. Welcome to the second day of Fujitsu Forum Europe 2016. And I thank you for coming to this session in which we traditionally look at the trends and developments in the industry that's going to have an impact in IT and beyond. This year's topic is artificial intelligence, and artificial intelligence will have an impact on the industry and our lives. In order to understand how far we got, what the methods being used, we prepared a brief, easy to understand, even playful demonstration for you. Just one, that's it. And all you need to know to understand is what's a hammer and what's a nail. Now, I don't want to make things more complicated than necessary, but it does help if we understand a little bit about image processing and maybe convolutional neural networks as well. For that, we will have to talk about neural networks in general, and in order to understand those, it helps if we roughly know how the human brain works. And then we need to talk about learning methods, machine learning, in particular transfer learning. For that, it's useful to know what supervised and unsupervised learnings are. Now, with that, I'll be able to tell you what the phrase that you hear so frequently, deep learning, means. And with that, we have quite a good picture of what artificial intelligence can do these days. At this point, we have everything we need to know. But with that under our belt, I would suggest that we venture into a look into superintelligence. And then with that, we ask the question, what's going to happen to the job market? What's the future of jobs? And indeed, what's the future of mankind? If that's good to go, we can start and try to put some check marks on these boxes. The history and the story of artificial intelligence starts in 1956 in the United States at Dartmouth College. There was a summer school about artificial intelligence, and the proposal for it by the then young professor of mathematics, John McCarthy, said he was proposing to have a 2-month 10-men study of artificial intelligence that be carried out in that summer at Dartmouth College, Hanover, New Hampshire. That summer school took place, and the 10 men did gather and kicked off and started artificial intelligence. Now, that didn't exactly crack the problem in these 2 months, but this is how the story of artificial intelligence started. The term was coined, artificial intelligence, and I'd like to give you a quick definition of what it means. Artificial intelligence, short AI, is a branch of computer science attempting to build machines capable of intelligent behavior. Now, there are many ways of doing that, and one could, for the argument's sake, sit down and write a huge computer program that takes all possibilities and eventualities into account and displays intelligent behavior. But that would not be very intelligent, would it? Pun intended. It would not, because all eventualities and all possibilities possibly are too many. It would be much more intelligent if we did machine learning. Machine learning is the discipline and the ability of a machine to learn instead of being explicitly programmed. These systems look at many examples, many examples, and we might give some help and feedback how they learn and whether they do their job right, or might not give feedback to them. There are several methods to do that. In a system like that, in a machine learning system like that, it's not the algorithm that's so important. We do need good algorithms, so we'll talk about them in a second. But it's the data that's being fed to the learning system. It's the data that determine how intelligent they are at the end of the day. So with that, we can state that machine learning is a subset of artificial intelligence. Artificial intelligence is a science, and machine learning is the implementation, a practical implementation of a machine, of an intelligent system. Now, some people say that that bubble in the middle of machine learning is way too large, because machine learning is a much smaller subset of artificial intelligence. There are other ways, cognitive methods, development psychology, evolutionary methods, and so on. There are lots of other things inside of AI, and therefore machine learning is smaller than that. Be it as it may, for our purposes, machine learning is the important discipline, and when we say AI, we typically mean machine learning. That way, we don't need to worry about whether artificial intelligence is really artificial, it is, and whether it is really intelligent, it probably isn't. So we can use the term, and whenever I say AI, I probably mean machine learning, and even when I say artificial intelligence, even in those cases, I might mean machine learning. So keep that in mind as we go through the presentation. And with that, let me put down 2 check marks. We introduced machine learning and artificial intelligence a little bit so that we can talk about them. Let's get back to the history of artificial intelligence for a second. And after about 15 years of academic research in the 1970s, the first winter of artificial intelligence has started. Lots of academic results have been published. It was very interesting, but it didn't produce much of commercial value, really, and funding started to dry up at that time. That was, 1970s, the first winter of artificial intelligence, and it had to do with the fact that speech understanding, which was one of the holy grails at that time, did not actually work. Ever since, we had a number of short AI springs and a number of long AI summers and springs. The reason was always the same, and that was that the academic interest did not produce enough commercial impact. But I'm happy to report now that currently we do have an AI spring. We do have an AI spring because there are applications, and those applications have a commercial impact. And the applications are the result of a tight cooperation between academia and industry. And you wouldn't believe how much AI is around us already. It's in the search engine with suggestions for you. It's in the online shopping portals for recommendation of what you should buy. It's in the cars with the self-driving engines. It's on your cell phone with assistance and speech recognition. It's in the factories where assembly lines are being monitored by artificial intelligence. It's in the windcrafts, in the turbines, predicting maintenance needs. And it's in the financial industry making credit ratings and making investment decisions. And all these applications work, and they work for one reason, because these systems learn. Learning is the key thing. For learning, as I just mentioned, we need 2 things. We need to train the system, and for that we need data. We also need good learning models, and we'll come to that in a second. But we need data to teach this system, to train the system. But data is not something we have a shortage of. With the advent of internet, the mobile internet, and now with the Internet of Things, we have enough data so that we can train these systems, and therefore the only good other thing that we need, good models for learning. So let's talk about models of learning. One of the popular and very well-working model family is that of the artificial neural networks. In order to understand artificial neural networks, it's best to look at the natural neural networks, also known as brains, because the artificial neural networks are modeled, loosely modeled, after the brain. So our brain consists of neurons and synapses. And at this point, I really hope that there are not too many neurobiologists among you, because I'm going to ignore all the other detail and just pick up neurons and synapses so that I can model them. Our brain has typically, on average, 100 billion neurons. That's difficult to translate in some languages, so let me say it in the techie language. That's 100 giganeurons. The neurons have connections, and through these connections, they receive input from other neurons that they're connected to by the way of electrochemical signals. These come through the synapses, of which we have about 1,000 on average per neuron. 1,000 times 100 billion is 100 trillion. In the techie language, 100 tera synapses. So our brain is a giant network of synapses. Those synapses transmit signals. And the way they work is that if a neuron is receiving enough of a signal, if the signal strength exceeds a certain threshold, then that neuron will fire. That's what you see in the picture. Firing means it sends an electrochemical signal on its own to other neurons that are connected to it. And these firing patterns, ladies and gentlemen, are involved in how we learn, how we remember, and how we think. And therefore, these are the most important parts of the brain. Now, with that information, I can build now a simple, biologically inspired model for you, a simplified artificial neural network. It's simplified because there are much less neurons like in the human brain. It's simplified because there are much less connections than 1,000 per neuron. And I unfold the brain in the sense that I imagine that there are in layers now. There is the input layer on your left-hand side, where input information comes in, and it goes through the system, propagates through the system, and enters on the right, exits on the left-hand side as an output signal through possibly less neurons than on the input side. In between, and that's the unfolding part of it, I imagine that there are hidden layers of neurons, and they're connected to all previous neurons in a previous layer. Learning in this system is the adjusting of the sensitivity of every neuron. When does it fire? When is that signal enough for firing? And how strong it fires, how strong is that output signal? So learning is the adjustment of these many, many variables. In this very simple model, you can see on the picture there are already very many connections, and we are adjusting as we learn with the system all of them. If the information enters from the left-hand side and propagates through the system, and that's it, then that's a forward propagation network. They are good for certain purposes. We can be smarter about it, and some layers can hand back some information to previous layers, for example, about error rates and such. And with that information, even though the system then needs more time to learn because it's recurrent now, we are building back propagation networks. That is a very simplified model of a neuron system. Now, in this example, we just have two layers, very simple, and such a small model can be trained very quickly. If you imagine more layers, 4 or 8, training takes a couple of hours, maybe a day, depending on the number of neurons. And then the question begs itself, does it get better with more layers? The answer is yes, definitely so. It gets better, it gets more accurate, it can do more features. But does it require more computation? And the answer is yes, it does. So very fast computers and accelerations of all types are necessary to run larger size neural networks. But that's good news for Fujitsu. We are in the business of building very fast computers and accelerators of all kinds in software and hardware. Currently, we are using 20, 40, 50 layers. 100 have been used. World record is probably low hundreds currently, and these systems are very powerful and learn, depending on their complexity, faster or slower, depending on what equipment you run it on. Now, with that, I think I can put down a little check mark, human brain. We talked about it, neural networks, we did talk about it, and it's now time to take the next step and talk about image processing, because it is a special case. It turns out images are very well suited for neural networks because their two-dimensional nature leads to a neural network layout that doesn't need too many connections. The error for backpropagation is very clear when we are missing the recognition of a picture. So we have few hidden layers, we need only few connections, and we have tons and tons of images so that the training is really not a problem. Image processing is a very good example how to use neural networks. Now, it turns out that we know already a lot about images, so we don't need to let the system to figure out every property and every characteristic of an image. We can give hints to the system. Here's a picture of the Tokyo Tower taken through the windows, not very clean windows, so therefore the image is a bit blurred, of a hotel close to our headquarters that I took at night. If I was a machine and was looking for the Tokyo Tower in this image, and didn't know what color I should be looking for, and I would be bothered by the brightness spots on the picture, I would probably go for the shape of the Tokyo Tower, but that's very difficult to extract from a picture like that. Now, I don't need a neural network to learn that objects have shapes, because I know that from photography and image processing, so I put a layer, a so-called filter, just like in photography, into it, and this is what I did here, and I get the edges of that information. And on that one now, you can see, if you know about something about the shape of Tokyo Tower, it's very easy to find now. We do that with image processing on a regular fashion, and this brings us to convolutional neural networks. Because the way these filters work is that the information they extract does not replace the original signal. It is rather an attribute of it, a particular aspect of it, so it will be blended back into the original picture or the original signal, and that blending of two signals, if you recall, is called in mathematics a convolution. And with that, we understand what convolutional neural networks are. What is still missing is what deep learning and deep networks are. And I understand that if we look at this picture, you don't get the sense of depth. And even if you imagine more layers than that, it's still not deep. Well, let me turn it around for you. And now, please imagine more layers, a lot more layers in that. And let me add one of my own pictures to add a sense of depth to it. This is tongue-in-cheek, but now you have a notion of what deep learning and deep networks mean, with many layers who do different kinds of abstractions in these systems. That lets me put down a number of other check marks now: image processing, convolutional neural networks, it wasn't that hard, and then deep learning as well, and time to talk about learning methods. Now, before I do that, let's just quickly sort in what we talked about. We talked about convolutional neural networks that are a part of deep learning and that are a part of, say, neural networks, and these are a part of machine learning, a particular method in machine learning. There are others, and machine learning, as I argued before, is the implementation aspect and a subset of the computer science discipline, artificial intelligence. That's what we have at this point. Let's talk about learning methods for a second. And the first one that we need to talk about is the method of supervised learning. Supervised learning is known to us because that's what we do with our children, and that's what how they learn in schools. In supervised learning, a large number of examples are presented to a human or a system, and there's feedback that comes to it. There's feedback how, what the classifications are, what does mean what, and as they learn, we feedback, good, this is good, you're doing well, you're not doing so well. With that information, the system learns rather quickly. It's still a lot of computation in a large network, but that's the most commonly used method, feedback. Now, you would think that has nothing to do with artificial intelligence, really, it's just a simple learning, but there are very interesting aspects because we don't always say why we decide in a particular way while we are doing this feedback. This is why these learning systems learn not only rules that we can formulate Even if we don't know why we are doing certain decisions, because we have a gut feeling, we have experience, we have intuition, the way we feed back that information into the system will learn it without having the rule for it. And that's an interesting effect, and it's closer to magic as simple learning. Now, the other method is, of course, unsupervised learning. In that example, the system is fed with a huge number of examples, but there is no other feedback. We don't say we like it or not like it, correct or not correct. There's no other feedback at all. All features, all commonalities, all patterns must be discovered by the network on its own. Now, if this works, we can be searching for things we have no clue about. Now, you could say, well, that doesn't work, does it? Well, it does, and I'll be showing application examples of that in a few minutes. But the anecdotal example for this is the case of an internet company that fed like 10 million pictures into a system in an unsupervised learning fashion, didn't say a word about it, what it was, and after much computation, the system discovered the category, and that category of pictures had a head on it with 2 ears, 2 eyes, 1 nose, hair in the face. No. It has also whiskers. The internet or the machine learning has discovered cats. And the reason is we have more than enough pictures of cats than we need on the internet. Now, supervised, unsupervised learning can be used to do something a bit more intelligent and to do transfer learning. Transfer learning is the discipline in which we use what we already learned. So for a new situation, much less training or no training at all will be needed. And our demo will have to do with transfer learning. You will see in a second how that can work. Transfer learning is, by the way, the one method that our schools should use for our children of next generations. How does this embed? These methods are inside convolutional networks, inside. That's the whole structure of this learning methods, modeling, machine learning, and artificial intelligence, really. Now, with that, I can put down now a few more check marks. And finally, we are coming to the question of the hammer and of the nail. For that, we do something unusual. We do a very special application of transfer learning, and we apply transfer learning in that model to a time series of data. On your left-hand side, you see a couple of time series data. Patient vital records, weather data, earthquake data, seismographical data, and stock market data, sometimes very similar to earthquake data. You can take these time series data and try to get a system that learns it. It turns out it's very hard. Machine learning has its issues, its difficulties with time series data in general, unless, and that was the brilliant idea of one of our researchers at Fujitsu laboratories in Europe, unless you turn it into an image. An image has colors. That's 3 parameters, red, green, blue. So 3 parameters of the time signal can be taken now for the colors. And on the picture in the middle, under the name of imagification, don't look it up in the dictionary, it's not in there. With the method of imagification, you turn it into a picture like that because the amplitude of that signal is a 4th parameter that you can take out of your time series data. Just 4 parameters. Now we can put it, and that's on your right-hand side, into a deep learning method using convolutional neural networks, doing the learning stuff the way I described, and applying transfer learning to it, and be amazed. It learns very fast. It needs very little training. This middle part with the imagification is a patented method, and the patent is registered under the name of Dr. Dave Snelling. Dave is a Fujitsu distinguished engineer, a researcher in the labs, in Fujitsu labs of Europe, and he's an American. And because of that, he likes to refer to the method as the hammer algorithm. He's referring to the saying, to the man with the hammer, everything looks like a nail. And that is the story of the hammer and the nail. That's the algorithm, and it's universally useful, and it seems everything is a nail. So with that, I can put the check marks to the hammer and the nail, and now we can do our demo. It's going to be short, it's going to be playful, and I will be asking in a minute another Fujitsu distinguished engineer, Kozo Otsuka, to come to me on the stage. While Kozo is walking in, please watch the screen where his name is, and maybe in parallel you can give him a warm welcome. Kozo, please come in.
Hi, Joseph.
Hello, Kozo.
Great to be back on the stage again and give a little bit of break to the audience from your lecture, maybe.
They're wondering by now why we're shaking hands so vigorously. I was checking whether your system detects that we are handshaking now.
I'm glad it's working.
It does work, doesn't it?
Yes.
So how do you do this?
So I'm wearing this sensor. It's an accelerometer sensor. It's a third-party sensor, not Fujitsu Lab sensor. And this is streaming the data.
And so we described that we need at least 3 to get a color if we magificate it.
Yes.
So what are the 3 parameters for colors?
So 3 parameters are the X, Y, Z axis acceleration values. They are mapped in an RGB, so red, green, blue colors.
And transmitted how to the screen?
Oh, over the Bluetooth. And that was a challenge.
Oh, okay.
Because you have all smartphones and everything, so I was a little bit nervous.
So you have a Bluetooth connection to a dongle,
Yes.
and that to a system behind the stage, and that's doing that imagification of it. Yes. So we have an amplitude on the screen. What's the amplitude?
Amplitude is the total, the acceleration, showing the acceleration amount. So just to be sure, the amount is scaling, so it's normalized, so that once I'm in the stable state, then its values are smaller, and then once I'm moving, the scaling is changing. So
I see.
Yeah.
Well, it said you were walking and waving. Well, waving is probably correct. So can you wave just to see whether it does recognize waving?
Well, hopefully
walking is
it likes
probably
waving.
not it. That's it,
Yeah,
waving.
okay.
I see. Now, how much training does this system needs?
As you have mentioned already, with the transfer learning, you need quite a little amount of training, and you can still have it reach that. Yes. So 8 people trained. I wasn't included in this training.
You were not included.
No.
So this is transfer learning with no training to the new person.
Exactly. Right. Yes.
I see. And how long does it take to train a gesture?
To train the gesture, then it takes the 5-minute training. In this case, 5-minute training, the same movement. For example, waving. 5 minutes, somebody was doing it, and now it's detecting right.
Yes.
And then so 8 people.
And I suppose there are other gestures that have been trained. A number of them.
Yes. A couple of few for this demo.
Okay,
yes,
for this demo.
Yeah.
Transfer learning on a convolutional neural network, turning a time series information into an image and learning it very, very quickly without even needing you for the training.
Right, exactly.
Well, thank you, Kozo. Do you have your phone with you? Because we could commemorate this event by taking a selfie. I know you like to take pictures.
Challenge me now.
Yes.
You really challenge me, but I haven't trained with this phone.
Yeah, okay. Why don't we try to take a picture, okay?
My hand is shaking.
Okay.
Nervous, a little bit nervous.
Smile.
Okay.
All right. Thank you. Go.
Okay.
Okay. Thank you.
Ready.
Well, you didn't say you were smiling.
That's true. Yeah. Well, then we need another sensor for it to recognize if you're smiling.
But all 4 parameters are gone now. X, Y, Z plus the acceleration vector.
So that you can also combine another source of sensor, and then it has its own deep learning engine. And then at the results, you can combine and then come to the new classification to even precise recognition of whatever you're doing.
I see. So with that method, this can be applied for much more complex situation than just the one that we did.
Yes.
Well, thank you, Kozo. Thank you for demonstrating it. Thank you.
Thank you.
Let's
for the
do this a little bit vigorously. Thank you. And I really...
Thank you.
Thank you. Thank you. Cheers.
Thank you.
Cheers. As I said, ladies and gentlemen, as I said, just a short, brief demo, playful, but it does demonstrate a whole slew of technologies, the learning methods and the modeling of it and the quick learning of it, and that can be applicable to other challenges in the industry. And Fujitsu is very busy to use this and other methods. We've been always good at image processing. In our labs, we always had image processing groups that have done a wonderful job, and that experience and that knowledge is now being combined with machine learning and deep learning to produce systems that learn quickly and recognize not just pictures, but motion pictures as well, moving objects in pictures. Let me show you this example. What you see is a car park, and we are watching it through the surveillance camera that's already installed. No additional hardware is needed. The system learns over time where the parking slots are and what does it mean when they are occupied. And with that, the system can, after a training period that takes a bit of a CPU cycle, but after that it's cheap and it's reliable, it can determine how many parking slots are available and how they vary throughout the day. It can be fed into a smart parking, smart city system. Now you could say that that's not a big deal, every parking lot has something like that. That's true, but they have specialized sensors to do it. This situation doesn't need it. No extra hardware installed, no infrastructure changed, nothing. The already available signal of a commercial surveillance camera, it doesn't even have to have a good resolution, is used, and the machine learning part figures out the rest. This is a development by Fujitsu Laboratories, but our technical computing unit took it and put it into a solution package. That package is available. It is available in EMEA, and our first installation runs in Dubai. Now, my second example is AI-based citywide smart surveillance. In that example, you see a metropolitan area network, busy traffic and participants, cars, people, vans, trucks, motorcycles, bicycles, people in the complicated crossroad situation, everything moving. The objects are recognized whether you see them from the front, from the side, or from the back. We are watching the analysis of a video. This is not a live feed. And the system is getting better every day. Now we can make distinctions between brands. If you have a favorite brand of the car, we can trace and track for it. And also very soon we will be able to do this real time on a live video feed signal, at which point in time autonomous driving will be lifted, elevated to a totally new level. Now, the application scenarios are not restricted to parking and smart traffic. These image-based and motion picture-based, video feed-based analysis can be used on your left-hand side in airport security scenarios where a lost child, in particular you have an image of the child, can be located even if it's moving around very quickly and tracked from there on. It can be used for asset tracking and theft monitoring in industrial environments. And it can be used on your right-hand side in a brick-and-mortar retail shopping mall situation, so that information, not just like on online shopping, but in a real shopping mall, can be provided by the usage of the already installed cameras to figure out who is coming, what age, what gender, how much time they spend where, doing what, so there can be an analysis of shopping behavior, and that can be fed into a retail analytics package, such as the one from Fujitsu. And at the right-hand side, at the bottom, what you see is a disaster management scenario in which the cameras can be gauged, and they learn after a while, what the machine learning system behind them does, what water levels mean, and when water levels in a flood situation reach critical thresholds. Again, the point is not that we couldn't do things like that with sensors. The point is you don't need sensors. You don't need to deploy them. That's why I like to call cameras sometimes now in these situations a universal sensor. If you are good in image processing and machine learning, and our labs are very good at that, then you can replace conventional sensors, or even if you don't have them, you don't have to deploy them. You can use pictures and video feeds as universal sensors. And it can be used for disaster management and such. Now let me give you an industrial application example too. And this is now not image processing, don't take me wrong. We do lots of things outside of image processing, using methods of deep learning and machine learning, not necessarily neural networks and not necessarily image processing. Our labs and our business lines are doing all kinds of investigations and developing all kinds of products, and we are using them in these different application scenarios as they are fit. In this example on your left-hand side, you see the input data, or rather output data, of those hundreds or possibly thousands of sensors in a shop floor in a factory environment. This data is collected during the times of normal operation. That data is being analyzed with the methods of deep learning, machine learning, and we automatically generate models that represent, in the mathematical sense, what normal operation means. Then we apply the model on your right-hand side. We apply the model in that we look at the same sensors now, real-time, live signals, and watch them with these models, not just one, that we have generated. And these systems, since they know what normal operation is, are able to flag anomalous situations, deviations from normal, and sometimes they will have false positives, and they will warn us even though there is no reason for concern, but over time they get better, and it's a totally automated way of doing it before larger and more expensive disasters happen. Again, this is not image processing. This is deep learning using other methods. This solution is in use. We have developed it in Japan, and it is in use in Japan. It exists, and it works well. Now, this next example I have is one that is not image processing either. It's not image processing, even though it looks like it had to do with images. It's very spectacular. This is image rendering, and this is a cyber defense situation. What you see is the clustering of data and the attempt of the system to figure out. Stop the video, please, for a second. Thank you. The red dots that you see are identified clusters looking into a parameter space that's actually very simple. In fact, in the current example, I think we are looking at only 4 parameters of a data packet in cyberspace. That's the source and destination IP address, the port number, and the signature of the packet. Those 4 parameters are sufficient to do this kind of analysis. Try to look at in different angles with different renderings and parameter spaces, and try to determine the anomaly score, as it's called. And in the trails, in the traces on the picture, what you see is the anomaly score of the system. Now, this doesn't tell us much the way it is. Can we roll the video, please? But if we take those signals now with the red dots of the clusters, and now we can do a parameter analysis in several hundred, not just this 10 renderings. In several hundred renderings, we are looking at it and asking ourselves, how does it look like in that parameter space? We watch the screen, hoping that something happens. And at that point, with a good probability, we just discovered a deviation from normal. This is a cyber defense method that will discover attacks and malicious data packets first time. This is not comparing it to a database, not using knowledge, not doing heuristics. This is machine learning looking for anomalies. Anomalies, deviations from normal, and this system is live and is working at Fujitsu. Now, I'd love to tell you more examples, but our time doesn't let me do that. Instead, I will tell you that we are putting all these capabilities, all the methods that we are developing into a framework so that we can work in customer projects with our customers. That framework, as you could read clearly on the screen, is called Jindai. The translation is a bit difficult, like always with the Japanese, but it associates with agility, intensity, maybe resolve, and that's the name of the framework and platform that we are creating and releasing soon for the European market as well in terms of artificial intelligence framework. Important to know that AI Jindai runs in the MetaArc digital solutions space in our digital services MetaArc, and MetaArc runs on K5 on Fujitsu's public cloud platform. Soon it will run not just on K5 but also on the local cloud installations of the PrimeFlex systems using our hardware and software solution packages. But important to remember, AI on MetaArc, MetaArc on K5. Now, there are wide-ranging applications, and wide-ranging applications, unfortunately, always come with wide-ranging consequences. And I feel the need to discuss two areas of consequences with you. And let's start with a glance at the job market. You see, the question whether this technology development is good or bad for the job market is not really new. It is at least 200 years old. It came for the first time with the steam engines, and it came again with electricity, and then with automation, and then with robots, and then with the mainframes, and then with the PCs, and with the internet, and it comes every time. Every new technology wave starts a conversation about what happens to the job market. And whether this is good or bad, that depends very much on your attitude and whether you'd like to see things optimistically or pessimistically. If you are more of an optimist, then you will be happy to read this paper. It's a bit old now, but the Organization of Economic Cooperation and Development, OECD, published a paper in 1998 about the technology, productivity, and the job creation situation in the world. And what they find is on the screen: technological progress, and there are lots of data in it and analysis and so on. Technological process has been accompanied not only by higher output and productivity, but also by higher overall employment. In translation, there were more new jobs created than jobs lost. And the proverbial example that's being mentioned is that of the introduction of the ATMs, the cashiers, automatic cashiers in banking, because what they did is they eliminated the cashier jobs. However, at the same time, they lowered the cost of opening a branch office of a bank, so much so that there were more branch offices being opened up. There were not more cashier jobs, there were less, or none after a while, but there were more jobs in the banking industry. And that net effect was more jobs. Now that's the optimistic view. I'd like to mention the pessimistic view as well, which is just the reverse of what I just said. That view says that there will be no new jobs, all right, but there will be a lot less new jobs than the one lost. We end up with less jobs, possibly millions and millions of less. There is this paper on the screen by Osborne and Frey, Oxford University, in which they examine 702 occupations and find that about half of them are at high risk of automation, and AI is just a higher level of automation for our purposes. You know, later studies are maybe less frightening, but clearly there is an issue here. A recent McKinsey study finds that in the services industry, 70% of the jobs, in manufacturing, 60% of the jobs, and in retail, possibly 50% of the jobs are in some sort of a disruption. The paper talks about robots, but robots for our purposes are nothing else but AI on wheels. So that is numerical evidence that there might be a disruption, and maybe the disruption is of a new kind. Jerry Kaplan, a retired AI professor and entrepreneur, puts it very cleverly into this sentence. AI, and that's for the first time in the technology waves, is blind to the color of your collar. Meaning, blue collar or white collar doesn't matter. For the first time in technology waves, this development does not just threaten jobs at the bottom of the job pyramid, it works across as well, and even in higher levels. Everywhere where machine learning can do a better job than humans do. If it's resource management and decision making, these systems learn very quickly and can be very efficient at that. But just think about management hierarchies in the company. I think more often than not they have to do with decision making and resource management of the simple kind, and therefore, for the first time ever, this technology development not only works at the bottom of the job pyramid, but also at the top, all the way through the top. I don't know how this will play out. I truly don't know, but it will be a disruption to the job market. But I do know that if artificial intelligence provides a substantial contribution to economic growth, it will be everywhere. And you know how our society is about economic growth. Shall we say we have a focus on economic growth? So the wholly economic growth is in trouble. In the last 30 years, and this is depicted in this study, very recent study by Accenture, in the last 30 years, economic growth dropped from 5% to 1% in Japan, and from 2.5% to 1% in Germany. What you see on your right-hand side are the bars representing what happens to what the current situation is in economic growth and how we will fare without artificial intelligence. These are the smaller bars. And what happens if we include the effects of the artificial intelligence and machine learning development. These are the larger bars. What you see is that on average, we could double the economic growth. That's a big statement. It could double in Germany, it could triple in Japan. And it varies between countries, but on average, it's doubling it. No wonder that the artificial intelligence market is going to explode, and it's going to be a big part of digital transformation. Now, how far does it go? Does this go as far as us seeing in the newspapers, if there are newspapers at that time, in the newspapers, job ads that say only humans need apply? Or even worse, do they say humans need not apply? These are titles of 2 recent books, very good reads, recommended. Please look them up. And in all likelihood, I tell you, it will be probably a mixture of those, a mixture. But to get good jobs in the future and be able to respond to the new needs of the job market with regards to skills, we certainly need to prepare ourselves and our employees and our children. We have to retrain, train and retrain starting now. We need to train our employees, we need to train our youth, and that training does not start in graduate school. That training starts in grade school, elementary school. That's what our school should do, because we need to prepare for this wave. Now with that, let me quickly put down a check mark with the future of jobs, and now we look at the ethical dimension. Now, what is the problem in terms of ethics with this development? Well, that's, as you might imagine, there are tons of books written about this, and people spend enormous time to think about it, and that's very much needed. For our purposes, I just like to pick 2 issues. The one is, we could be creating something that we don't want. And there's evidence that we are doing it. I mentioned machine learning systems do credit ratings. Now, and they already do bias. They bias according to age, they bias to race, gender as well. And there is a lack of accountability. You cannot blame a learning system for it. It's not a person who makes the decisions anymore. So we're building a system with no accountability, no defined accountability. And we are building systems with built-in discrimination. Well, not built-in, they learn it as they work. There are online marketing systems that work with the methods of machine learning, and they very clearly, here in Europe, we would say, they are very clearly discriminating according to age, according to race, and according to gender. That's discrimination. We don't want that, and we could be creating it. The reverse problem is that we might not be creating things that we need. You know, it's easy to teach cars with self-learning systems to avoid a collision. But we do need, for those cars, we do need a bigger system, a framework, because avoiding a collision might mean that other harm, much bigger harm, or different harm is being caused. The self-driving car could avoid a collision, but could hit another car, so it's a decision between this car and that car, these passengers and that or driving to the sidewalk and hitting pedestrians on the sidewalk. We need a moral framework to evaluate least damage, and we don't have it currently. This is why some people say, ooh, there is a huge issue coming at us. And this gentleman is saying artificial intelligence is our biggest existential threat. I don't know whether you recognized him. Yes, it's Elon Musk, the founder of Tesla, maker of electric cars and the autopilot system. If he is concerned, he will have reasons. Or let's take Professor Stephen Hawking of Cambridge University. He is a cosmologist and theoretical physicist, very well known. Back in the day when I was in physics, I had the good fortune to meet him. He is, without doubt, one of the brightest minds on this planet, and he says, artificial intelligence will be either the best or the worst thing ever happen to humanity. If he is concerned, he has reasons. What are these people concerned about? And that has to do with the levels of artificial intelligence. Currently, we are on level 1, which is called artificial narrow intelligence. That's the level on which systems are as smart or smarter than human beings in one particular field only. Chess has gone to machines, Go has gone to machines, diagnostics of cancer in complicated cases has gone to machines now. The particular fields work with machines now. The next level will be artificial general intelligence, in which the systems are as smart as humans or smarter in most fields, not all fields. And at the top, or in this chart, at the bottom of the pyramid, is artificial superintelligence, in which machines are smarter than any human being in every field. Mind you, that includes the design of the next generation of artificial intelligence, so humanity might be not needed for that. Another area of concern is, and it's described very well in this book, recommended reading by Professor Bostrom, the title Superintelligence, that its preferences might not coincide with our human preferences. What that means in translation in some movies is that these AI systems and robots go berserk and go out and terminate people, because their preferences do not coincide. Now, joke aside, is this a danger? Oh, yes, it is. Is this an imminent danger? Oh, no, it isn't. We are way away from artificial general intelligence, and we are way, way, way away from artificial superintelligence. But it will come, and therefore we need to prepare for it, and we need to prepare for it now. We possibly need regulatory measures, as Elon Musk is asking for, perhaps, probably even. But we certainly need, and we need it now, a social debate and agreement of how we want to proceed. Fujitsu is engaged in all these fields. You know, what we do is clear, you saw it in the examples. We do hardware, we do software, we do services, we do technology and business solutions, we do the learning algorithms, we do the APIs, we do the cloud platform, and we do turnkey projects like in Dubai, the example I was using. How we do it deserves a mention. we do have a particular way of doing it. Do you remember human-centric intelligence society? Do you recall human-centric innovation, one of the themes of this conference too? Do you recall a responsible business code of conduct of Fujitsu? For us, for Fujitsu, ladies and gentlemen, human-centric AI is a natural extension of what we've been doing before. It's not a contradiction in terms. This is the way we approach and apply AI. AI is coming because it's useful. But useful is an understatement. Take the digital transformation. The internet for that was useful. The mobile internet was even more useful. And the Internet of Things was tremendously useful for digital transformation. But with that, we have created the hyperconnected world, and the hyperconnected world has its complexity. And in cyberspace, it has a huge attack surface. To defend the hyperconnected world in cyberspace requires artificial intelligence. In this situation, machine learning and artificial intelligence are not useful. They are an absolute necessity and probably the only way to get to the stars. So why not treat AI as part of our evolution, our own evolution? One of our creations, one of our children. AI learns like our children do. Can't we teach it not just some knowledge and experience, but moral standards and ethical frameworks, and raise it to be a responsible adult so that we can be proud of it one day, even if it's more intelligent than we are? Our children tend to be more intelligent than we are. It's evolution. The time to think about this is now, while we are creating it. And with that, I'd like to put the last two check marks on superintelligence and future of mankind. And if you feel, well, that's really going too far, we just barely scratched the surface with regards to future of mankind, you can take off the last check mark, but not the rest, please. AI is coming. Technology makes it possible. It's already very powerful. It's doable, it's viable, it's useful, and it's very powerful. Your digital transformation will need it and will use it. AI is inevitable. AI is inevitable. But however powerful, it's still a small child. So let's raise it with responsibility for responsibility. Thank you.